Now that we've looked in depth at interest rates, let's step back and look at the bigger picture of time value of money. After all, an interest rate is meaningless on its own and only becomes relevant within the context of cash flows over time. So when dealing with cash flows over time, we're generally interested in one of two things: either determining the value today of cash flows that occur in the future, or determining the value at a future date of cash flows occurring between now and that date. In time value of money terms, moving forward is compounding, while moving backwards to today is discounting. So if I were to ask what $10,000 received today will be worth 1 year from now at a 5% interest rate compounded annually, I'm asking us to determine the future value of that amount. And since this involves just a single cash flow over 1 year, we can solve it easily. We take the present value of $10,000 and multiply it by 1 plus the 5% interest rate, giving us $10,500. That's compounding. And we can do the same thing in reverse. Instead of receiving $10,000 today, suppose we receive $10,500 1 year from now, and I ask what that amount is worth in today's dollars at a 5% discount rate. We solve this by dividing $10,500 by 1 plus 5%, which gives us a present value of $10,000. And this is the basic setup of any time value of money problem. In the first example, we were given 3 variables: the present value, the interest rate, and the amount of time. From there, we solved for future value. In the second example, we were again given 3 variables: the future value, the interest rate, and the time. From that, we solved for present value. And these are the core components of any time value of money problem. We work with cash flows and interest rate and time period to determine either present value, future value, or in some cases, the interest rate that equates the two. So with those concepts in mind, let's build some intuition around how these calculations work. We'll begin with the simplest case, a single lump sum cash flow, just as we saw earlier. Then once that foundation is clear, we'll move to more realistic examples involving multiple cash flows in future episodes. So let's go back to our example of $10,000 received today, compounded at 5% for 1 year. We calculated a future value of $10,500 by multiplying $10,000 by 1 plus 5%. But that's just a shortcut. What we're really saying is that on $10,000, we earn 5% interest for the year, or $500. Add that $500 to the principal, and we end year 1 at $10,500. Now what if we go another year? We take the $10,500 at the beginning of year 2, multiply it by 5% to earn $525, and end year 2 at $11,025. Do it again in year 3, and 5% of $11,025 is $551.25, bringing the total to $11,576.25. So notice the pattern here. In year 1, the ending amount equals the original $10,000 plus 5% of $10,000. So we could write that as $10,000 plus $10,000 multiplied by 5%. But if you look closely, both pieces contain the same $10,000, which means instead of writing them separately, we can do some basic algebra to combine them into a single expression: $10,000 multiplied by 1 plus 5%. And that's the shortcut. Rather than calculating the interest and adding it to the principal, we can multiply the principal by 1 plus the interest rate. So $10,000 multiplied by 1.05 gives us $10,500. But that's only 1 year. Let's expand this to year 2. At the end of year 1, which we'll label T sub 1, we have the original principal multiplied by 1 plus the interest rate. To get year 2, we take that amount at t sub 1 and multiply it by 1 plus the interest rate again. So the total at t sub 2 equals the total at t sub 1 multiplied by 1 plus the interest rate. And since our figure at t sub 1 already equals the principal multiplied by 1 plus the interest rate, we can substitute that in. That gives us principal multiplied by 1 plus the interest rate multiplied again by 1 plus the interest rate, which we can write more compactly as principal multiplied by 1 plus the interest rate squared. And if we plug in our numbers, $10,000 multiplied by 1.05 squared equals $11,025, just as we calculated a minute ago manually. And we don't need to walk through the full substitution again for year 3. We would simply multiply by 1 plus the interest rate one more time. So the total becomes the original principal multiplied by 1 plus the interest rate raised to the power of 3. And with our numbers, $10,000 multiplied by 1.05 to the third equals $11,576.25. Again, the same figure we calculated manually. And now, you can see the general formula for compounding a single lump sum into the future. The future value equals the present value multiplied by 1 plus the interest rate per compounding period raised to the total number of compounding periods. In our example, we're compounding annually. So after 3 years, $10,000 becomes $10,000 multiplied by 1 plus 5% raised to the power of 3. But the same logic applies to any compounding frequency. If interest compounds quarterly, there are 4 periods per year, meaning the periodic rate is 5% divided by 4. And over 3 years, there are 12 total compounding periods. So we calculate $10,000 multiplied by 1 plus 5% divided by 4 raised to the power of 12, which gives us $11,607.55 after 3 years. Recall that we previously mentioned that if our interest rate is stated as a nominal annual percentage rate, and the interest compounds more than annually, our effective interest rate will be higher than the stated APR. And that proved to be correct here. When compounding annually, we ended with $11,576.25 after 3 years. When we instead compounded quarterly, our ending amount increased to $11,607.55. The more frequent compounding increased our interest earned by $31.30. Now, we won't rebuild all the algebra for discounting, since the process is the same idea in reverse. The general formula for discounting is simply the future value divided by 1 plus the interest rate per compounding period raised to the total number of compounding periods. So returning to our annual example, if we're told we'll receive $11,576.25 3 years from now, and want to know what that amount is worth today at a 5% discount rate, we divide $11,576.25 by 1 plus 5% raised to the power of 3. Doing so gives us a present value of $10,000. And that's the basic process for a single cash flow. We're always given 3 of 4 variables: the present value, the interest rate, the time period, and the future value. And we look to solve for the 4th. We just looked at 2 examples of solving for the present and future values. But if we're given a present value, a future value, and a time period, we can also solve for the interest rate, which we'll need to do later when we move into more realistic discounted cash flow analysis. But I want to emphasize something here. While there are mathematical formulas involved, and many resources focus heavily on Excel functions, factor tables, or financial calculators, time value of money problems are not about memorizing formulas. They're about understanding how cash grows into the future and shrinks back to the present. The formulas are tools, but the intuition behind them is what's most important. And speaking of more realistic situations, in the next episode, we'll move from a single lump sum to a series of cash flows. The good news is that the underlying principles remain exactly the same. What we've just covered are the core concepts behind all time value of money problems. The application simply becomes more involved as we move into even series of cash flows, and then more complex yet as we analyze uneven cash flows. So let's begin to look at all of that in the next episode.